Hello friends, welcome to Kishor Premier Academy, one of the most premier institute for GATE, IES and PSU examinations. Hello friends, in this video we are going to discuss about some preliminary topics of electronics device and circuits. In the preliminary topics, we will first discuss about the temperatures. There are three types of temperatures that will be discussed in this electronics device and circuits. First one is the absolute temperature, and this absolute temperature is defined by 0 Kelvin temperature, which is equals to minus 273 degrees centigrade. The second temperature that is needed for this electronics device and circuit subject is the room temperature. So the room temperature is defined by 300 Kelvin temperature, that is equals to 27 degrees centigrade, and the third temperature, that is the ambient temperature, and this ambient temperature is nothing but 290 degree K or 290 Kelvin, which is nothing equals to 17 degrees centigrade. So these three temperatures will be frequently used in the electronics device and circuits. Generally, all the communication system works or operates in ambient temperature. So this was the first topic of preliminary topics. The second topic that we'll discuss in this preliminary topics is the thermal voltage. In the thermal voltage, it is very important. In thermal voltage, we will discuss about the voltage equivalent of temperature. So what do we mean by this voltage equivalent of temperature? It means, suppose we have a device. Let us consider that this is an semiconductor device, and this one is the input port, and this is the output port. Now at any temperature, let us consider a temperature T1, and at this temperature, if the input voltage, if I give, that is Vi at T1, then there will be some output voltage at the device V0 at T1. Now, if I change this temperature to T2, then the output voltage will change by some amount and we will get V02, and this V02 is nothing but due to the change of the temperature T1 to T2. So we are seeing that we are changing the temperature of the device and we are getting an equivalent voltage change V01 to V02 in the device output. So we can say there must be some voltage equivalent of the temperature, and that voltage equivalent of the temperature is given by the term Vt. That means this thermal voltage is denoted by the term Vt, and this Vt is equals to Kt by Q, where K is the Boltzmann constant and it is given by 1.318 into 10 to the power minus 23 joule per degree Kelvin, and the T, capital T, is equals to the temperature, and Q is the electronic charge. The value of the electronic charge is equals to 1.6 into 10 to the power minus 19 coulomb. So these are the variables that are used inside the thermal voltage equation, which is denoted by the term V suffix T. Now, if we substitute the value of Q and K, because this Q and K value are constant, so if I replace the value of Q and K, then it will turn out to be 1.318 into 10 to the power minus 23 joule per degree Kelvin into capital T divided by 1.6 into 10 to the power minus 19 coulomb. So if we calculate this equation, we will get capital T divided by 11,600. So we'll get a Vt equation like this: T divided by 11600, and the unit of this equation will be volt. So we can see here that the thermal voltage Vt is proportional to the temperature, which is very important with respect to the gate examination, that the thermal voltage or the volt equivalent of temperature is proportional to the temperature. Now, suppose if the temperature is 0 Kelvin. So at 0 Kelvin temperature, if we find the value of Vt, then it will be 0 divided by 11,600. So it will come out as 0 volt. So at T equals to 0 Kelvin, we can see that Vt value is 0 volt. Similarly, if the temperature is at room temperature, and we know that the room temperature is 300 Kelvin, so at room temperature the thermal voltage Vt will be 300 divided by 11,600. 600, then it will come out to be 0.0256 volt, or we can say it as nearly equals to 26 millivolt. So from this equation we can see that at T equals to 300 K, the thermal voltage value will be 26 millivolt, which is very important conclusion of the thermal voltage. So far we have seen that Vt value, that is the thermal voltage value, is given by capital T divided by 11,600. So from this equation we can see that for large variation in temperature, we will get very small variation in thermal voltage, because capital T is divided by cut start, because capital T is divided by a large number, that is 11,600, and this 11,600 is a very huge number. So if there is a change of T, cut start, so if there is a large change in the value of T, we will get a very small change in the value of Vt, because the T value is divided by a large number. Now the second conclusion we can draw here is that at standard room temperature, that is at 300 Kelvin, or we can say 27 degrees centigrade, the equivalent thermal voltage Vt is equal to 26 millivolt. These two conclusions are very important with respect to the gate examination. Now we will discuss the third preliminary topic. The third preliminary topic is the electron volt. This electron volt is denoted by EV. This electron volt is the smallest unit of energy in electronics device and circuits. That is, electron volt is the smallest unit possible that is used in the electronics device and circuit, and it is also smaller with respect to joule unit. Now, what will be the definition of the electron volt unit? For that, let us take an example. Suppose we have a metal plate like this. This is the A metal plate, and let us take another metal plate B like this. So these are the two metal plates. Now, if these two metal plate A and B are connected by the external potential in this way, suppose I have connected the external potential of 1 volt in this fashion, then we know that this is the positive terminal and this is the negative terminal. So from this negative terminal in the plate B, there will be accumulation of electrons here, accumulation of electrons here. Now these electrons will start to flow in this direction, in this way. So this A plate will be of positive potential. That's why these electrons are coming from this metal plate B to metal plate A. Now, from this case, we can define the unit of electron volt. What is that unit? Unit is that the energy required or gained by an electron moving through the potential of 1 volt. It means that these electrons which are moving between the plates B to A, they are moving due to the applied potential of 1 volt. So during the movement they will gain some energy, and that energy will be termed as 1 electron volt. That is the energy gained by an electron moving through a potential of 1 volt. And this is called the 1 volt 1 electron volt energy. Simply 1 eV. So this was the definition of 1 electron volt energy. So this 1 electron volt energy from the definition can be written as the electronic charge Q into the applied potential difference. So this is the applied potential difference So from this equation we can put the value of Q. So we know that it is 1.6 into 10 to the power minus 19, and there will be a mod value into applied potential difference, means we have applied 1 electron volt, so 1 V. So we can see after calculation we will get 1.6 into 10 to the power minus 19 coulomb volt. This coulomb volt unit is nothing but 1.6 into 10 to the power minus 19 joule. So I can see that 1 electron volt energy is equals to 1.6 into 10 to the power minus 19 joule. And this is a very important relationship between the 1 electron volt energy and joule. So we can convert the electron volt energy to joule and joule to 1 electron volt. Now from the definition we can already see that the electron volt denotes the kinetic energy gained by the electron. Or we can say that the potential energy, that is PE, lost by the electron. So from this statement we can write that the kinetic energy that will be gained by an electron will be half m v square, where this m is the mass of the electron and this v is the velocity of the electron. Similarly, the potential energy that will be lost by the electron can be written as Q into V, where Q is the electronic charge and this V is the potential difference that we have applied. Now, from the definition, we can see that electron volt denotes the kinetic energy gained by an electron or the potential energy lost by the electron. So from this definition we can write that the kinetic energy that will be gained by an electron will be equals to the potential energy that will be lost by an electron. So if I put the value of kinetic energy, that is half m v square, and if I put the value of potential energy Q into capital V, so it will be half mv square equals to Q into capital V. From this equation, if I find the value of small v, that is the velocity of the electron, it will be v small v is equals to 2q capital V divided by m. Now this equation will give the velocity of the electron due to any applied potential of capital V, and from this equation sometimes get numericals has been framed and the unit will be meter per second. So this equation gives the velocity of the electron when a capital V potential has been applied across the two plates. Now let us come to the fourth preliminary topic, that is the energy gap. So this energy gap is denoted by capital EG. This energy gap is also denoted by the band gap energy. Band gap energy. Generally, semiconductor materials are of two types. Generally, the fundamental semiconductors are of germanium and silicons. These are the most available semiconductors in the practical world. So, if I see the value of germanium and silicon bandgap energy, it will look like this, that germanium and silicon has bandgap energy of Eg at T equals to 0 Kelvin. It will look like it has a value of 0.785 electron volt, and for silicon it will be 1.21 electron volt. That means at T equals to 0 K, germanium will have smaller bandgap energy and silicon will have a higher bandgap energy. Similarly, the bandgap energy at T equals to 300 K, it will be 0.72 electron volt, and of silicon it will be 1.1 electron volt. So we can see that as the temperature increases, the bandgap energy of the material decreases. This table is the practical data of the silicon and germanium. So from this table we can see that the temperature is increasing but the bandgap energy is decreasing. So we can say that in semiconductors the Eg value decreases with temperature. That is, Eg value is proportional to 1 by temperature. This equation or this information can be written in an equation form, that Eg, that is the bandgap energy at any temperature T, capital T, will be written as Eg at T equals to 0 K minus beta 0 into capital T in electron volt, where this beta 0 is denoted as the material constant of the semiconductor, and it is having a unit of electron volt per degree Kelvin. For germanium, this equation of EGT will be of the form of like this: Eg of capital T, that is the bandgap energy at any temperature T, will be 0.785 minus 2.33 into 10 to the power minus 4 into capital T. That is, the beta 0 value for germanium is 2.33 into 10 to the power minus 4. Similarly, for silicon, we can write this equation as Eg at capital T will be 1.21 minus 3.6 into 10 to the power minus 4 into capital T. So this 3.6 value into 10 to the power minus 4 is the beta 0 value for silicon. So all these data are the practical data. So this is all about the preliminary topics of electronics device. Thank you. Last of all, Do not forget to subscribe and like our channel to get more videos like this. Thank you.